the temperature of the liquid and the intermolecular forces of the liquid. So more intermolecular forces will give a lower or higher vapor pressure. It would give a lower vapor pressure. And how I'll explain that is, if you have molecules in here, and they're like, they have strong intermolecular forces, it takes more energy for them to leave the solution. So they're going to want to stick together more, so there won't be as many gas particles, so there's going to be a lower vapor pressure. However, higher intermolecular forces means higher boiling point for the same reason. If you have stronger forces together, it's going to require more energy to boil those out. Does that all make sense? Okay. Evaporation. So sometimes it's tricky with the wording. There could be a question about evaporation with regards to how fast the molecules vaporize, and that's like analogous to vapor pressure. So you just say that is affected by temperature and the intermolecular forces. However, they could ask a question saying something like, what factors affect how much liquid leaves over a period of time? And it's kind of tricky because those sound like the same thing because it sounds like how much liquid evaporates, but this takes into account condensation because evaporation, you're having some molecules go out and then you're having some condense back in. So there's like a net equilibrium. But if you do something like increase the temperature, those also do it, but wind speed, air moisture, air pressure, and surface area, those all affect how much liquid leaves because they lower the condensation rate. Does that make sense? Any questions on that? Okay.
Can you say that again?
Okay, so, I know, I think it's confusing. Okay, so they could ask a question about evaporation rate with regards to how fast molecules leave. They could also ask a question about how much liquid leaves, like bulk liquid leaves. And that would be affected by, the bulk liquid would be affected by wind, air moisture, air pressure, and surface area, because all of those lower the rate of condensation. So that would like basically shift the equilibrium to where you're evaporating more than you're condensing. Whereas temperature and intermolecular forces don't affect condensation rates, but they do affect how many molecules leave. Yeah?
So intermolecular forces are inversely proportional to vapor pressure. Is temperature the same or is it directly proportional? Like if temperature goes up, does vaporization pressure go up too?
Yeah.
Okay.
Yeah. Okay.
So the vapor pressure has the condensation, or does evaporation also have molecules going back in? Or like evaporation is just
Molecules leaving.
Molecules leaving. There's none coming back in. Like
You're not asked about them coming back in, but they do come back in, but you don't worry about that unless it says how much liquid will leave the fastest, and then you would account for wind, air moisture, air pressure, etc.
But vapor pressure is the one that like reaches the equilibrium, right?
So when vapor pressure is equal to air pressure, that's when it starts boiling. Questions on that?
Yeah.
Yeah.
Did you just say that condensation rate and evaporation rate are not related at all? Before I know that work is that
I know that the temperature and intermolecular forces of the liquid affect the evaporation rate. I know that wind speed, air moisture, air pressure, and surface area affect the condensation rate.
Why does it say rate of evaporation?
Because there's no distinction between using the words evaporation rate versus how much liquid leaves over a period of time, because that's basically evaporation, rate of evaporation. But he says he'll be very clear on the test which kind he's asking for.
What's the relationship between evaporation rate and pressure?
Vaporization pressure, they're proportional.
So the
Higher the vapor pressure means you're evaporating more. Questions? Okay. Distillation. So really quick, this is just a way of purifying liquids purifying liquids when you're starting with a solution of different liquids. And the most common way to do it is you have your solution of all the different liquids, and you boil out the ones that have the lowest boiling point first. And those will collect, right, the liquid substance right here on the right, that's what boils out first. So what you'll do is you'll take the heat up to the lowest boiling point and boil out your first substance, and then if you have more you want to boil out, you go up to the next boiling point and then the next one. That make sense? Routes laws, okay.
Yeah.
Will we have to do one of those graphs that we did in smart work?
It's all multiple choice. So no. Okay. Routes laws. Okay. So Routes law of partial pressure says that the total vapor pressure of a solution is equal to the weighted average of each liquid's vapor pressure. So you can see that, so we have P equals XA, PA plus XB, PB, where P is the total vapor pressure of solution, and XA is the mole fraction of solvent A, and PA is the vapor pressure of pure solvent A. We're gonna do a practice problem in a minute, so this will make more sense. And this is for when all of your solvents are volatile, which means they'll create a vapor pressure. Questions on that? We're gonna do a question in a second. Okay, and then there's the other Routes law kind of, and that's when you add a non-volatile substance to a solvent. That'll be something like salt or anything else that he says is non-volatile. But he says you just need to know salt. And how you calculate the new vapor pressure is you basically dilute the old vapor pressure. So you find the mole fraction of the solvent and you multiply it by the pure vapor pressure of that solvent. Okay, and then there's a question right here. Okay, what is the vapor pressure when 0.685 moles of hexane is added to 0.564 moles of benzene? The vapor pressure of pure hexane is 573 torr and benzene is 391. So just try that one really quick. It should take you about a minute. Yeah, so because you know it's also because it happens. That's the thing. I can just go back to the last one. I'll give you guys 30 seconds. Okay. Sorry. Okay. Quiet down. Thanks. Okay. So how you do this problem is you want to find the mole fraction of each liquid. So what you do is you want to first add up the total moles. So that would be so n total would be 0.685 plus 0.564, and that's going to give you 685. Okay, 1.249. Okay, so now you're going to take the moles of hexane and divide that by that. So that would be 0.685 divided by 1.249. And you're going to multiply that by the normal vapor pressure of pure hexane. So that'd be 573. Okay, now you're going to add that to the mole fraction times the mole fraction of benzene times the normal vapor pressure of benzene. So that would be 0.564 divided by 1.249 multiplied by 391. All right, and what'd you guys get for P total?
490.
490? Yeah? Yeah, that's what I got to. 491, I think. Okay, so that's how you do that if they're both volatile. Does that make sense? Questions? Okay, so remember that. Osmosis.
All right, so osmosis is kind of, the only thing you can ask about this really is a conceptual question of whether or not you kind of understand what's going on with osmosis. So it's the movement of solvent, so not solute. One mistake that I remember I made when I was thinking about this, I was like, oh, it's the salt is moving to make the, or whatever the solute is moving to make the concentrations equal, but that's actually not true. It's what the solvent is, so the water or whatever else you have the thing dissolved in, is going to move across a membrane from low concentration to high concentration in order to dilute it more. So the concentrations will be equal. So the osmotic pressure is the pressure that is required to oppose the osmosis. So make it so that the pressure, so it doesn't osmose, if that's a word. So for example, if you had like two tubes, kind of a U-shaped tube thing. I'll draw it out right here. We can't see that. All right, let's do it here. If I had like a U-shaped tube that like looks like this, so I have like a semi-permeable membrane right there, and there's like a liquid over here and a liquid over here. And so I can go and do osmosis through here, but this pressure up here, this gas up here, is the osmotic pressure. Does that make sense? So it's the pressure that's on top of the liquid that's kind of forcing it down or keeping it from going up. So like if for example, I had a higher concentration here and a low concentration here, and the liquid moved through here, the osmotic pressure would be what was keeping us down. Does that make sense? And so that's pretty much the best explanation you can get for that, yeah.
Does the pressure go down when you